Magnus Egerstedt. He is currently Julian C. Hightower Chair in Electrical and Computer Engineering. He has associated appointments with the Mechanical Engineering, Aerospace Engineering departments, etc. He's also he's well known for his work in network controls and network coordination. He also received I need to get the name right, a Razzini Award from American Control Society, and he has been awarded the Alumni of the Year Award from KTH, Royal Institute of Technology. So, and today he's going to talk about long-range autonomy with applications to persistent environmental monitoring. And here's a sneak peek. He'll talk about sloths in this presentation. So, what does robotics have to do with sloths? Please take it away, Magnus.
Thank you. I got one clap. That's a good start. Two, there we go. No, I appreciate it. I'm really, really excited to be here. I have actually never visited Yukon before, and I thought I had a great ride from the airport. It was a little ominous because I was driving through this forest and there was nothing, and then the university. So that was exciting. And then this morning, it was a winter wonderland that I woke up to. But I'm originally from Sweden, so this is nothing. I'm excited to be back in a place where you have proper snow. So thank you for that. Indeed, I am going to talk about long-range autonomy. So the idea really is, if you send out a large team of robots, let's say on the campus here, over an entire year to monitor things like how much snow you're getting in April, how does that change the design paradigm as opposed to when you do something once in a lab and it happens to work? Meaning, if you deploy things over truly long time scales, how does that change the design paradigm that you should be using? And we already heard that I'm going to talk about sloths. I'm going to draw a lot of inspiration from biology and ecological principles for how we think about things that are out for long periods of time as opposed to things that do. So my normal day job is I make teams of robots do something cool once. I get the video, I write the paper, and then I'm done. But now if I'm going to deploy it for, let's say, a year, how does that change the design? Before we do that, though, I wanted to say a few other words about my other day job, which is I'm the director for the Institute for Robotics and Intelligent Machines at Georgia Tech. And we're a large-scale research institute, rather similar to the research institute that invited me to come here. So I've had a really good day today trying to learn how you're organized, how it's different, what I can take back to Georgia Tech and do better, and what I think we already do better. So for that, let me tell you a little bit about what's going on in the world of robotics. If my clicker works. There we go. Here is robotics. This is classic robotics. You have very large manipulators doing this over and over and over again on the manufacturing floor. So this particular piece is for the body shop part of a car assembly process. And these robots are really good at doing this over and over again. This could be spot welding or painting, and we're good at it. The most important thing, though, here is this stuff around it. These are large, scary mechanical beasts where you don't want to be anywhere near them. I mean, these robots typically have very few sensors on them in terms of detecting what's going on. They certainly don't reason about, if there's a person here, I should move the car door a little bit differently. So, classic robotics is that. And one of the most important things is the cage. And what's happened over the last, I want to say 2 decades, is the robots are escaping the cages. The robots are coming. And as part of that is, what is going on? Well, so here is actually, I've started calling this the Great Robot Migration. So here's what's going on. The robots are leaving Rome, and actually where they're going is not Carthage. They're going all over the place, right? So we're seeing a lot of robots on the farm fields. So precision agriculture has become a major force in robotics. Part of it is farms are not that complicated, meaning, corn rows are nice and straight, and there are very few stray puppies and bicyclists running around. We're, of course, seeing warehousing being largely robotic. Amazon Robotics now, they claim to have what they call completely dark warehouses. So these are warehouses where there are zero people, no people, only robots. And I have a former student who works for Amazon Robotics, and I said, is this really true that you have completely dark warehouses? And he said, nah, it's not exactly true, because people have to go in every now and then and clean up after the robots. So we're becoming cleaners for our robotic overlords. We see robots in our homes, on the battlefields, of course, in hospitals. We see medical robotics being a major driver. So when they're leaving their cages, they're going all over the place, and they're changing their morphology or their form. Robots are no longer these things. They are, flying, rolling things, slithering things. This is a robot I really like. It's a third arm that you can attach to a drummer, and now you can play even more expressive drum solos. This is a Da Vinci surgical robot. These three, by the way, are all Georgia Tech robots. We have lots of them. But one of the things that's really fascinating when this robot migration is going on is if you start with this machine, this is a Newtonian machine. To understand what this thing does, you need equations of motion. You need to live in the world of Sir Isaac Newton. But the second the robots start reasoning about the world, right, you need all of a sudden this Alan Turing. You need to understand things about perception. You need to understand things about learning. You need to reason at a much higher level about the tasks. And one of the things that's fun about robotics and hard is you need to make these two men, Alan Turing and Sir Isaac Newton, play well together. So this is what we refer to as an example of a cyber-physical system. What's even weirder than that is these robots are not only out there, they're out there next to people. So all of a sudden, we need this guy. This is Sigmund Freud. So to really go after big questions in robotics, you need to understand controls and dynamics. You need to understand perception, learning, and AI, and psychology. Right? Human-robot interaction is a major thrust. NSF has something called the National Robotics Initiative that is entirely focused on trying to bridge these three gaps. And this is what makes it kind of interesting and challenging and satisfying to run a robotics institute. So I just want to show you how we are organized in order to actually address this. So we are lined up around three thematic areas. One is autonomy. So these are robots that are out in the world making decisions based on stuff they see. These may be rolling, hopping, swimming, flying, walking robots. Then we do quite a bit of work on human augmentation. So these are robots that are used to make the human experience richer. This could be orthotic or prosthetic devices. This could be exoskeletons. Also medical robotics fall under this category. And then we do a lot of work in collaborative robotics. So robots and people doing things typically in the manufacturing setting. And we are one of the largest institutes on the planet. So we have 85 faculty members in robotics. We've started a robotics PhD student recently. We're now up to 70 robotics PhD students. And we do around $33, $34 million in sponsored research every year. So that's the kind of institute I run. And I've actually, like I said, learned quite a bit today from talking to people involved in the institute we have here. So having said that, let's actually get back to the talk. When I give talks, a lot of times, I talk about how do you actually structure interaction models for large teams of robots. So let's say that you're all robots. Congratulations. You're also kind of not that talented, to be honest. You can't see very far. You have limited communication capabilities, maybe limited processing capabilities. But I would like you to solve a task. Let's say I want you to form a circle. So how do you actually, with very, very limited information and only with local rules, move around in such a way that you form a circle? Or maybe more importantly, I learned that there is special artisanal Yukon ice cream somewhere on campus. So what if I sent you all out to get me ice cream? Please don't leave. But what if? Right? How do you organize yourself so that some of you go out, cover the area, look for ice cream. Some of you carry the ice cream, but then your hands are too cold, so you hand it over to the next person. What is the mechanism by which we do this? And 10 years ago, we really didn't know all that much about how to structure multi-robot systems. Fast forward to today, and we really have understood quite a bit. So a normal talk that I would give would talk about this, and then I would end with a slide kind of like this one. So here I have 15 robots that are, in this case, they're spelling grits, because I'm the director of the Georgia Robotics and Intelligent Systems Lab. And what we're doing is we're broadcasting what letter they should shape. R, actually let's do I. And they know the geometry of this, what I looks like. And then they need to figure out where should they go in the I, how should they assemble it in such a way that they don't collide. And in this case, it's based solely on sensory information, so no communication, with local rules. And again, let's say 15 years ago, we didn't know how to do this. Now we understand quite well what the right mechanism is for doing this. So this is a typical last slide. I think it's a good ending to a talk, right? Because we show robots doing interesting things. But what I've gotten really interested in over the last 5 years is this question. What if you wanted to do this out in the snow instead here? Or you wanted to do it in the fall, and then winter came, and there was snow, and then it stopped snowing, and then it's April, and it's snowing again. Right? How does that change the design paradigm? So one thing that's clear, first of all, is if I try to design my system so that I enumerate everything that the robots are going to experience through their journey through the snow, then I'm doomed to fail, because stuff is going to happen that we can't predict. Right? So somehow we need to be flexible enough to predict things that aren't part of the design. The other thing, I think, is forget about optimality. Right? So people, for instance, we are remarkably good at walking around an entire day without falling over. We can walk on snow, we can walk upstairs, some of us can walk with high heels. But we already know from biomechanics, we used to think that people were energy minimal, we're not. Then there was this idea that we're minimizing jerks, a third derivative, we don't. So now the idea is nothing we do seems to be all that energy efficient or optimal, but we're remarkably resilient. So some kind of notion of robust optimization, if I may steal from Matt here. For instance, I use my hands a lot. There's absolutely no reason to do that if you want to minimize energy, but I do it anyway, right? It's a huge waste of energy. But I don't fall over, so at least we got that. So some notion of robustness needs to be built in differently. And then there is a lot of free time. Right? The robots are just going to sit there most of the time. So what should robots with free time be up to? How do you think of the design cycle when you don't want robots to do a particular task over and over and over again? So that's really what the theme of this talk is. And I'm going to approach it through 4 different vignettes. I'm going to start by talking about something called the Robotarium. And then, indeed, I am going to talk about sloths, because why not? And then we're going to be a little technical for a bit, and I'm going to talk about composable barrier certificates for control design, and then we'll end with the robots in the snow. And this will actually make sense after a while. It won't quite make sense. But I want to start with the Robotarium. And it really starts again with this picture. I showed these pictures. Here are 15 robots and they're spelling grits. There's something that's missing when you show videos like this. There's stuff going on that's not in the camera or in the frame. First of all, there's a bunch of smart students and postdocs standing there going, woohoo, it worked. Right? The other thing is that these little dots here are actually reflective, what's called mocap, motion captioning dots. There's an entire $250,000 motion captioning system around this thing. And there are cameras up in the ceiling looking down. And these weird-looking robots they're kind of expensive. There's an awful lot of this stuff going on in the picture that's never shown. And I got increasingly irritated by the fact that it costs so much money to run and maintain a world-class multi-agent and swarm robotics lab. A, because I have to spend a lot of time raising money, but more importantly, there are only a handful of labs in the world that truly matter in this space. I'm going to claim that mine is part of it, but it's not because there's a handful of labs with good ideas. It's because there's a handful of labs with the resources to run a sharp, world-class multi-agent robotics facility. So I didn't like that. So I decided to solve it, and the solution is kind of obvious, right? You build a remotely accessible multi-agent robotics testbed. So I had this idea of, let's build one where we have a bunch of robots. People can just upload code, run experiments, and then get the data back. So I called that the Robotarium. And I went to the National Science Foundation, and I said, here's what I want to build. This is actually the Vienna Chamber Orchestra's concert hall with Harvard's kilobots on them and some random stuff and a GT logo on it. And NSF, they said, sure, do it. So this is what I built. Not quite the Vienna Chamber Orchestra. Actually, this was an early version. But the point is, we built a remotely accessible swarm robotics lab. Actually, now it's looking quite charming. So we built a facility that went live in August of last year with 120 ground robots and 30 aerial robots. And this was kind of became a big deal. I was on the front page of the Wall Street Journal with the headline was, this lab has no idea what its robots are doing. But the idea was very simple. Users upload code, run it on the Robotarium, and get the data back. The problem is, let's pick someone here. What's your name?
Evan.
Evan. You seem completely reasonable. Well, we don't know, right? So you upload code, and how do I know you don't break stuff? Even if I don't know, especially in the air. The problem is that stuff happens in robotics, right? So here's Evan. He's telling my robots to do something, and you weren't that reasonable. Yeah. Stuff happens all the time. So how do I make Evan be allowed to upload code on the Robotarium without him breaking stuff? And the biggest question is really a question of collisions, right? So how do you avoid collisions? This is, I think, the most famous robotic collision. This is the DARPA Urban Challenge 2007. Here's MIT's car, and here's Cornell's car, and they're autonomously driving into each other. They're still actually bitterly arguing over who was really at fault. But I also had a car in the Urban Challenge. It was a beautiful Porsche Cayenne. Let's see if volume works here. So here is it. Yeah, it was great. It was doing really good. And then we can laugh about it now, but this it's a year and a half of my life that just anyway, point being is collisions are bad, right? So let's not have collisions. Let's have Evan upload his code, and somehow what we're going to do is we're going to wrap safety behaviors around it. So the standard view in robotics is you add a collision avoidance term, and there are as many collision avoidance terms as there are roboticists. That's one of the first things you do. You write down. The problem is that they're all hacky, meaning, let's try 1 over distance squared or something. And they work fine if you're building a robot that's out on a museum somewhere, not slamming into paintings and people. But as the robot density goes up, if you haven't thought through what the collision avoidance behavior should truly look like, all the robots will be doing is avoiding collisions, because that is just going to start dominating. So we actually had to take a step back and reimagine what collision avoidance should actually look like technically. So let's say you have a robot. So there's a differential drive, whatever, control affine in this case. So X would be the position and U would be my input. Here's one robot, here's another robot. They're on their way to collide, but I'm going to color the arrows green because it's still mathematically possible to avoid a collision, even though they're on a collision course. So this is still fine. Let's not touch it yet. Another way of saying that is if you take the joint state, so there is some set S, which as long as the joint state is in that set S, then it is possible to not collide. If you get to the boundary, then it means you better take evasive maneuver, evasive action. If you don't, you're going to collide. And if you're on the outside, you may not have collided yet, but at least you know that there's nothing you can do to avoid collision. Another way of saying the same thing is, let's say that there is some function h, scalar function as a function of the state, that's positive when you're in the interior of this set, it's 0 when you have to take action, and when h is negative, there's nothing you can do to avoid collision. So this is one way of encoding this, and then one can do this. So we wrote down the following optimization problem. So Evan, you get to be U sub n. At a given point in time, Evan wants my robots to do this. This is his control input. And I'm going to say, no. you get to do U, which is as close as possible to what you're proposing, such that don't break stuff. So this is and this is, by the way, all pairs. You have to make sure no one collides with anyone, right? This is a reasonably looking optimization problem. The only problem is that it's complete nonsense, because X and U are not coupled at all. So here, the optimal solution is, well, U equals to UN and be done. The way you have to couple it is somehow through the dynamics of the system. So what we need to do is to come up with a differential version of this that couples the dynamics of the robots to the constraint. And we're going to do that using something called barrier certificates. So here's the idea. H positive means all is good. Right? So H is actually going to be called the barrier function. And we want to make sure that H remains positive at all times. Well, look at this. What if magically we could do H dot equals to some function. This is a class K function of H. You can think of this as H dot equal to negative H, for instance. There's a whole class, and all of these classes result in H decaying down asymptotically to 0. Let's assume that we could say that if H dot was equal to that, then H would actually decay down to 0 asymptotically. We're not going to do that. What we're going to say is, what now if H dot is greater than or equal to that? Then there's this beautiful thing called the comparison lemma that says that if H dot equal to alpha that decays down to 0, then H dot greater than or equal to that means that the green arrow or the green line is always above the red line. This is comparison lemma. All right, so this is something we would like, because if we could say that H dot is greater than or equal to negative alpha, we know that H is always positive. So what we're going to do then is we're going to couple the dynamics of the system here into this. So H dot is the H dx x dot, which is this thing, which you can write in a fancy way using Lie derivatives. This is just H dot along trajectories of the system. So now the condition then becomes this thing should be greater than or equal to negative alpha. Let's take this, slide it over. So the condition on U simply says that this thing that looks complicated, but it's a function of x, so forget it. The only thing we're caring about is U. This thing times U has to be greater than or equal to that stuff that's a function of x. That is the barrier constraint. So in that case, what we do is we say, Evan wants to do that. We say, not quite. This is what we're going to do. We're going to do U such that this holds. And then it turns out we don't have to care about all pairs. You only have to care about robots that are close by, because it seems silly to care about all of them. If we do that, then we actually have a theorem that says that if the robots start safe, meaning inside the safe set, they always remain inside the safe set. And Evan gets to do as much as he wants, subject to don't break my stuff.
Yeah, a question.
Yes?
But Evan is not by himself. There are others that have different controls.
Yeah. So what's going on here is this only works if, so I'm a robot, Evan is a robot, if we're both solving the same problem and we're playing by the same rules. If I start misbehaving, then this is not a good solution anymore. So this is exactly right. This assumes that we're all solving the same problem together because we're good robots. And if we do that, we get things like this. Let me turn off the volume. So we're going to start with 4 robots. Evan wants them to swap positions. Sorry, I'm picking on you all the time here. So this is what they're asked to do. Right? And now we're wrapping these barrier certificates around what's going on. So when they get to within striking distance, they evade each other. And we didn't tell them to go counterclockwise. All we said is, here's the constraint. Conduct yourself accordingly. And I like it because it seems reasonable. This is a collision avoidance routine that is provably minimal in a certain sense, which is in this sense that we looked at it. And, you can do more robots, and it turns out that the way to negotiate traffic jams is with traffic circles. Going back to your question, what happens if someone is not playing along? Well, it's still safe. It's just not minimally invasive. So here's a big robot that refuses to play along, and these little guys go, oh, shoot, run. So it's provably safe. It's just not minimally invasive anymore. It's not a particularly efficient avoidance routine. We even put it in the air, right? So here we're going to see an example of these 4 robots are spiraling around, and then one of my students, Lee, is dragging this one, trying to make it crash into the other ones, and the barrier certificates kick in So it's impossible to actually make them collide. So point being is when Evan uploads code now, that's what happens. And since we went live in August 2017, we've actually, this number is close now to 400 research groups all around the world have run experiments. And I'm kind of excited about it, that we're actually beginning to reach a large group of people that would otherwise not have access to sharp robots. In fact, this is a plot that I'm particularly excited about. We have research labs from every continent except Antarctica around the Robotarium since. So please, by the way, quit this Yukon stuff, move down to Antarctica, start a research group, and run code on the Robotarium so I can go check. Anyway, fine. Neither here nor there. Why is this matter to the robot in the snow? Well, for that, we clearly need to talk about sloths. In fact, let's start talking about leaves. Let's say that you're an animal and you like to eat leaves. You're what's called a folivore. Leaves are actually really bad foods. They're structurally complicated and they're toxically protected. I mean, plants want you to eat their fruits and their nuts. They don't want them to eat your leaves, right? Because that's how you get energy. So leaves are complicated things, which means animals that are folivores need to have a long digestive tract, a big gut to break down this horrible food. They need to be cows and elephants and giraffes. Big. Cows even have multiple stomachs, right? Okay, so if you want to be a folivore, and you also, for some reason, want to climb trees, that's complicated, because if you want to climb trees, you cannot be too big. So there are actually very few folivores that are arboreal, that are tree-dwelling, because clearly, if you want to be as big as possible to break down this crappy food, yet you need to be small so you don't fall out of the trees, it's a very tight ecological niche. It turns out that there are only a handful of species on this planet that are arboreal folivores, and they're all between 3 and 8 pounds, and they all look like this. So this is a sloth. This is actually a two-toed, but there are two-toed and three-toed sloths. This guy is called the slow loris. This is a koala bear. There are a few others, the red panda, maybe. They're all the same size, and they all just don't do anything because their diet is so energy poor because they don't have enough gut to break down these leaves. So they better not move because they don't have the energy to support what they're doing. So I got a little fascinated by sloths. I went to Costa Rica, I started reading about sloths, and for instance, this guy, actually the three-toed sloth, that is the lazier of the sloth, just sits in the tree all the time, except every 8 days or so, climbs down and goes to the bathroom and then climbs back up. I don't know if you've heard this. So energetically, it's like running a marathon in order to go to the restroom. And it's also by far the most dangerous thing a sloth does. So it's like running a marathon while being attacked in order to go to the bathroom. So I actually I got in touch with John Powley, who is a sloth ecologist at the University of Wisconsin, and asked, why do they do this? This makes no sense. And he said, that's the wrong question. An ecologist always asks the following question. What is it in the environment that's forcing this behavior to emerge? Ecologists think about environmental constraints as the generator of behavior. So what I realized then is, by talking to John, is here is what the meaning of life actually is if you're an animal. So the meaning of life is don't do anything. Life is, by the way, completely meaningless. We're existential nihilists here. Sit on the couch as much as you can, subject to don't die. That's ecology. Right? So this involves, eat a little bit, mate. There are some other things that you want to do. But largely, this is an ecologist's view of life. Minimize energy consumption such that don't die. Which means that we should do that for our robot, right? This is what it means for a robot to be out in an environment for really, really long time, which is do nothing such that don't die. And the interesting thing is that we've already seen one constraint, which was this barrier certificate for not colliding. What if we now could add a bunch of constraints together to describe what this robot is doing? So what we need to do is we need to compose a bunch of these things together to describe a rich life of a robot out in the snow. So do nothing, subject to don't die. That to me is what long-range autonomy could be. So we now need some way of gluing these things together that makes some sense mathematically. I want to go back to the problem that we actually solved before. So this is u sub this d. This used to be n, now it's d. Let's pick on someone else. What's your name?
Renee.
Renee. So this is what Renee wants the robot to do. And I'm going, no, you get to do that. This is a quadratic cost in u. So it's a quadratic cost. And this is the constraint that we saw. It's complicated in x, but that doesn't matter. We just read in x and evaluate it. It's a linear constraint in u. So this is a quadratic programming problem. It's actually not hard to solve. So we can actually solve this in real time all the time. There are a few problems with it, though. One big problem is the theorem says that if u satisfies this, then you're safe all the time. It doesn't say that there always is a u that satisfies it. So you actually have to go back and verify that you always have feasibility. So in the case of collision, we always show that slamming the brakes is a feasible solution. So we knew that one always existed. The other problem is there is no notion of deadlock avoidance or task completion. This is not a particular. If you wanted to build the world's greatest collision avoidance behavior and you also got to say what the robots were doing the rest of the time, then this is not the way to do it. The problem is I don't know what Renee is telling the robots to do, so I can't predict into the future what's going to happen. I have to respond now. So that's why we're doing it this way. This is why there's no prediction. The problem is we have no notion of deadlock avoidance because we have no notion of what the task is except don't die, right, or don't collide. And that's something that you have to sometimes go in afterwards and tweak your H so that you actually avoid deadlock. The other thing that we don't know how to do is how do I take a bunch of these now and put them together in a mathematically meaningful way? So here, for instance, is something we could do. We could want to, if I have C1, which is, let's say we're a mobile sensor network. So C1 says, be close enough. You and I need to be close enough, eh? So that's C1. And C2 is, but we shouldn't be too close because then, so close enough means we stay connected, but too close means collision. So if you have two constraints and you want to do both, and then you hit the intersection, right? So geometrically, set theoretic, and is just an intersection, or is the union, right? The question is, how do we turn these things into H's that make sense? So what does it look like if I want H1 to be positive and H2 to be positive? What is the right mathematical object to make that happen? Well, you can take the min. If the smallest of H1 and H2 is positive, then you know they're both positive, right? So the min is actually a good and. So if I want to do H1 positive and H2 positive, well, then I just say and has to be, the min has to be positive. Okay, or should be a max, right? So if H1 or H2 is positive, well, it's enough if the max is positive. In fact, it's equivalent. So the or is the max operator. And then, of course, not becomes the negation. So now we have a full Boolean logic. So we can say things like and or not. We can do anything in a Boolean setting. This is not a linear temporal logic. There's nothing fancy going on because there's no notion of prediction here. It's all instantaneous. The only problem is that these operators are non-smooth and complicated. You can't take a nice derivative of a max, so instead you have to do some set-valued version of it. You can. So we have a non-smooth version that you basically replace equalities with set inclusions, technical detail. The point is you can actually start composing things together using max, min, and negation operators. So for instance, here's an example of 4 robots. We have a blue robot, a green robot, a red robot, and a yellow robot. And the blue robot, no one should collide to it. No one should collide to the green one or the red one or the yellow one. So H safe is safe to the blue one and safe to the green one and safe to the red one and safe to the yellow one. But then the green robot, well, it's asked to do this, green U, but it also has to be close enough to the blue robot. So safe and close enough to the blue robot. The blue robot has to be safe and close enough to the green robot. So now you have what's called the backbone here, when blue and green has to be close enough to each other all the time. And then the red robot has to be safe and close enough to the blue robot or the green robot. So it has to be connected to one of them. And same thing with the yellow. And this is kind of a messy specification. But the beautiful thing is when you just run this then, you get something like this. So this is what the robots are asked to do. But they can't because they're colliding. This is blue-green. This is always maintained. And these two are at least connected to one of them all the time. There are no collisions. And they're trying to follow the trajectory that have been specified as closely as they can. And I love this because this is rich behavior. This is rather complicated what's going on. And it's entirely driven by constraints. We didn't tell them much. We just said, hey, do all the... People write papers about connectivity, preserving collision-free coordination. We didn't have to do that. We just wrote a bunch of constraints. And to me, this is the robotic equivalence of climbing down out of a tree and then going back up. Well, to go to the bathroom and then going back up. It's complex, and it was driven by constraints. So I was very happy about this as a way of actually ensuring that we could get rich behaviors out. Cool. All right, so having said that, let's finally get to the robot in the snow. What should the robot be doing? Well, we were interested in this question of persistent environmental monitoring, where I want to spread you all out on campus to measure something, how much snow there is, say. So the question is, how do we do this? Well, first of all, we now know that you should just minimize energy. That's the first thing. And then somehow you should spread out in some good way. And there are different ways of thinking about the spread out. But since we're going full ecology here, why not look at the animal kingdom? So, for instance, this is actually Tanzania. There are different lion prides. And Craig Packer from University of Minnesota showed that they actually spread out according to what's called a power Voronoi tessellation, where you get a weighting based on the prevalence of prey and water. There's a termite mound or a number of them. They form these hexagonal shapes. There is a very influential work on something called the selfish herd. Hamilton wrote the paper in 1971 that showed that zebras, or if you move into the center of your Voronoi cell, then that's the right strategy for not being eaten. So we decided, let's do a coverage controller where we spread out using these kind of Voronoi ideas. So Jorge Cortes has a beautiful algorithm for doing the spread out. So you have a bunch of robots. Here is more interesting stuff, that's dark blue. Less interesting stuff is light blue. And they spread out based on where their neighbors are in such a way that they cover the area most efficiently. So we decided, let's do that. But we want a constraint. We don't want to tell the robots to do that. So here is what survival looks like for a robot in the snow that's trying to do environmental monitoring. First of all, we have don't collide with other robots. But then we also need to make sure that you never run out of energy. You always need to go recharge the batteries when they're too low. So we built a version now that has solar panels that need to go out in the sun and sunbathe and then go back in under the trees to do what they're doing. For the purpose of this talk, it's just a charging station. So the first condition says, don't be too far away, too close to other robots. And the distance to a charging station has to be a function of how much energy you have left. So that the less energy you have, the closer you need to be to the charging station. And finally, when the energy is very low, the distance has to be 0. So that's that. And now you got to do two other things. One is you got to cover the area, which we encoded as a constraint that said the amount of stuff in your Voronoi cell has to be above a certain threshold. So you have to have enough stuff in your Voronoi cell. That's what that says. And then charge, well, what we said is this is basically the distance to the charging station has to be a certain. So either you have enough area there, or the distance to the charging station is 0. And we started this, and it was beautiful. The robots spread out. Right? So now, and they're just sitting there doing nothing. And then as they were running out of, as the battery levels were going down, they went back to the charging stations, and then they just stay there for the rest of their lives. And the problem was this: either you cover or you charge. So why not charge forever? So what we need to do is we had to add another constraint to this h, so h also depended on the energy, so that once the energy is becomes equal to the max energy, then things happen to the charge that pushes you away from the charging station.
But this doesn't say altogether you have to cover entire space.
So, it doesn't say altogether you cover the entire space at all. And it also doesn't guarantee that we don't all go in charge at the same time. So, this is, I think, part of the, so we'll get to that, but part of the problem with instantaneously just minimizing the energy consumption is a very myopic way of doing things. But it's an interest, so I'm really interested in this idea of how far can we take this ecological idea of do nothing, subject to don't die. And we're going to change this in the next slide because it's actually not the right thing to do. But you're absolutely right. This does not say that we get a good coverage. All it says is either you have enough stuff in your cell or you're charging. That's all it's saying. And the theorem that goes with this says that the robots never run out of power. That's the only theorem we have. We don't have a statement about quality of coverage. So if we do that, we're going to see a simulation here with a bunch of robots. They're going to spread out. Here are the charging stations. And we're going to see, most of the time they don't move, right? So we're going to speed up time to 16 times. And then they're going to go back to the charging station and so forth. And as I was preparing the slides yesterday, I for the first time realized that there are actually little sloths in the background of the simulation that Gennaro, my student, did. So now they're spread out. This is what the coverage algorithm tells them to do. And then we sped up to 16, and now this is low on power. Safety is pushing this out of the way. These are still trying to do coverage control. Now this guy goes back, and now we're seeing that we're having two people coveraging at the same time. This one goes back out. And this is what you get, entirely driven by these constraints. And again, I like it because it's rich and complex, and we didn't tell them to do it. We just told them, don't die. And this is what we got. This is what we got out. We also put this on the Robotarium. Same thing there, right? We're going to speed up 16-fold because most of the time they're not doing anything. So here again is have enough stuff in your Voronoi cell, and then one of them is going to run out of battery and going to go back to the charging strip here. Robots that seemingly do nothing most of the time. And again, I personally am a big fan now of not specifying what they're doing, just specifying constraints that come from the environment. And it's a little bit of a different way of doing. It's actually a completely different way of doing control design. Normally, we say, here's the cost, minimize it. I'm not doing it. I'm saying, spend as little energy as possible subject to these constraints. And to answer Peter's question, the real way that I'm now thinking about this is this constraint should really be a constraint that says don't collide and don't run out of power. And then when we want to tell them to do something, we should specify again a desired controller. So for instance, we could actually specify a coverage algorithm on top of this to say, this is what coverage control gives us. Do that, but every now and then go and recharge. And in fact, in the Robotarium right now, since this is on 24/7, it's been on for 3 months now since the last checkup, this is what they do. So they go out, they do their stuff, and then some of them get pushed back to the charging stations. And when one gets pushed back, then the other ones come out. And this is, again, what Evan is doing. So this is still the survival constraint. But then the taskable missions sneak in through you desired. And there's a new NSF program that you may be aware of, you should be aware of. It's called Smart and Autonomous Systems. And they are still trying to figure out what this program is about, but it's really autonomous systems that are out for long periods of time, learning from the environment, learning from each other, learning to be ethical. And we propose this thing as an autonomy as a service concept, where this is just the robots are out there, and then the way you recruit them is through the you desired. The second call is coming out next week, apparently, so be aware of it. So with that, let me actually conclude. The first thing I want to say is, even if you didn't like anything about the talk, which, by the way, you have a way of expressing it, so extremely dissatisfied. Right? So even if you're extremely dissatisfied, can't see how you would be, it had sloths, but even if you were, the Robotarium is worth checking out. I mean, this is a place where you can actually upload code and run experiments. And we've had not only roboticists, we've had a lot of biologists use it. We have now a group of myrmologists, which is code for ant scientists, running experiments on it, which I think is really cool. The other thing I also want to push for is this idea of richness of behavior through constraints. I think is an interesting idea. By no means am I saying that we've solved all the problems. In fact, we haven't. But I really like this as an idea of generating interesting behaviors. And one thing in particular makes me happy. So if you want to do two things, right? You want to walk and chew gum at the same time. The classic way of approaching that is, here's a cost for walking, here's a cost for chewing gum. Let's add them together, or multiply this by 0.7 and this by 0.3. There isn't a natural way of combining costs. What you could do is you could do multi-objective optimization and get the Pareto optimal fronts, but then you still have to decide where you want to be on that front. This is not canonically natural. Combining constraints or sets is, you want to do this and that, boom, it's just an intersection. Right? So there is something canonically nice about sets that's not nice about adding costs. I'm still going to do a lot of optimal control, but there is something nice about this, I think, at least intellectually speaking. And then this here is the robots that do nothing. This actually looks like a picture, but it's not. They are moving, but this is what it looks like in real time, the video we saw that was scaled up 16-fold. So with that, if there was something here that was particularly exciting, it's probably due to one of the students or postdocs in my lab, or some of my collaborators. So let's thank them if you liked it. If there was stuff you didn't like, I suggest we blame the organizers for inviting me. So thank you.
Well, thank you for that talk. It was really exciting. It was a lot of great humor, and I think we all really enjoyed it.
Extremely dissatisfying.
Yeah, extremely dissatisfying. So we'll open it up for questions. We'll have a bit of time for discussion.
Yeah, how do you write the constraints in terms of U, like the ones in Edge? The first and second is that a mixed integer quadratic program? Can you convert it into that?
So the constraints, first of all, just plop out from, if you have a control affine system, so x dot is f of x plus g of x u, then life becomes very simple because u just plops out. So let me instead of me talking about math, let me show you. So this is what it looks like. So this is just saying h dot, which is this plus that, greater than or equal to that. And if the system is control affine, which any reasonable robot is, at least if you squint a little bit, then this is a quadratic cost in U, and it's a linear constraint in U, and there's nothing integerish about it at all. This is just
the Boolean operators.
So now the cool thing about the Boolean is I did not want to integer anything, so I replaced it with mins and maxes, because those operators are continuous operators. They're not differentiable, but they're continuous. So it allowed me to get things that I could just write down as a single h. It's just an h that involves mins and maxes. And then I can still, since I'm in the business of feasibility, right? I'm not trying to maximize or minimize something complicated here. I just want a feasible solution. Then if I can formulate my h as a continuous function, then we're all good. And again, h is a function of x. It's not a function of u. And the thing that I'm minimizing over is u that falls out here. So that is, I mean, if I wanted to minimize this with respect to x, then my life would be horrible and forget it. But it's not. I'm minimizing with respect to u. I should say another thing. So one thing, though, is when you do, how many people have taken a controls course? Good. Excellent. So we've learned different control designs. Let's do pole placement, or here's LQ, right? So here are weight matrices, or here's the specs with rise time and this. Where did this come from? Who picks the poles, right? Who picks the weight matrices? Who picks the overshoot? Someone always makes a decision in control design, and sometimes we forget that. There's always a decision to be made, and here the decision is H. And as you saw, there was a little bit of tweaking and what is the right H. That's where, finding the right H for a certain application is not so trivial. Collision avoidance is trivial, it's just don't be too close. But beyond that, it's not obvious always what is the right age. So there is an art, actually it's more than weights. H is almost a Lyapunov function. It's almost a control Lyapunov function. And just like it's hard to find Lyapunov functions, it's sometimes hard to find the proper H's. So I wanted to say that.
So do you have to enforce this constraint at all the x's?
Yep. And all time. So this is instantaneous, right? And this goes back to Peter's complaint, which is a perfectly good complaint, which is, why in the world aren't you predicting things into the future to get better performance? And yeah, why don't I? The reason we didn't do that is, I don't know what Renee is going to tell my robots to do. Her code is just, her view is, Renee, I'm talking about you.
Oh, yeah.
Yeah,
I'm
okay.
actually a librarian.
You're a librarian?
Yeah, I'm an engineering librarian.
Oh! So that's why I really didn't trust your code.
I do know some coding and programming.
Yeah, that's good.
I actually don't program robots, but...
But now you could, right? And even when your library code makes them do weird things, at least you're not going to break stuff. So that's why we're not predicting all the way into the future, because we don't have a model. I also like this idea of, if you deploy them over long time scales, stuff is going to happen that you can't predict. And this idea of enforcing safety at all costs actually makes a whole lot of sense to me. You may sacrifice optimality, but at least you get survivability.
Yeah, I'm very much intrigued by this control concept, this constraint concept. Two questions. One is that you got this idea is because of Robotorium.
Yep.
That you don't know the
Yeah.
So the follow-up question is that how do you reconcile this concept versus your control concept? So how do you see the future?
Yeah, this is a really good question. I mean, it came from a very particular problem that I had, which was the Robotarium. I didn't want the librarian Renee to break my stuff. And none of us want that. So there I had a real problem. And then I've actually spent quite a bit of time with ecologists now, because I do believe that if we're going to understand robots that are out for long periods of time, we need to understand the coupling with the environment, and that's what ecology is about. And this way of formulating seemed to fit very well with the ecological view of the world. So I like that. I like that as a generator or a starting point. Now, how do I reconcile it with control concepts? Really, this thing, it has to be different. Or, for instance, what if you, instead of doing this, is you minimize a v dot, so all of a sudden you have performance here, so you have a control Lyapunov function, for instance. So I think there is something you can do where you add performance here and add this constraint there. So I do think that they're not mutually exclusive. And I mean, to be honest, the way I would do coverage is not what I did in the previous section. I would do it by messing with this thing, where this comes from a coverage algorithm, and this is just a low-level safety wrapper around that control algorithm.
But if you, like your first video, you really want to be decentralized, you cannot do UD.
Yep, that's right. So I would then say that if I want to do a lab experiment where I spell grits, I should do what I did. But if I'm actually sending things out for long periods of time, let's say on a farm field, right, where I want my robots to live with the plants for an entire site, I don't care that much, I think, about the perfectness of the formation. I care more about the longevity of the system. Right? So I do think that I was trying to hint at that. I don't fully know what a formal theory of long-range autonomy looks like, but I'm trying to get to one where optimality or performance is secondary to survivability.
Very good.
Thank you.
Let me go next because we have this up. I was really intrigued when you made explicit that when you're dealing with the maxes and mins, you introduce you introduce non-smoothness.
Yeah.
What is the theory you're using for set value mapping around that?
Yeah. So really, what I write down is the normal. This constraints come. This is code for saying h dot, which is the time derivative of h, being greater than or equal to some function here. You can just think of this as minus. I actually use negative h cubed in all my... Cube turned out to be the greatest class K function in the history of ever. So this actually is h cubed. now when you have set-valued things, then h dot is not a point. It's now you get a vector or you get a set-valued thing. And you need this set to... so this becomes a set relationship where every point in that set has to satisfy that relationship. Luckily for me, my non-smoothness is rather minor, and it's only at the point where h1 overtakes where the switch is. It's not... So it just means that h dot now is a cone as opposed to a single direction. So but I am using these Clark generalized gradients too. Yeah. So that's what I'm using.
Fantastic.
Actually, I'm working with a guy named Jorge Cortes who eats this stuff for breakfast, and I go, okay, good.
Yeah.
I'm glad someone else did it for me.
Yeah, we should. It's really interesting. It's certainly aligned with a lot of work that we do with basically making up smooth derivatives for using the Clark.
Yeah.
For exactly this feasibility problem.
Yeah, and I mean it goes back to the question about mixed. You could have gone mixed integer, but then life becomes hard. Yeah. And since I'm not trying to do that complicated of things, I'm just trying to do a little bit of Boolean algebra. There are easier things to do, and still you still get the same formulation. Yeah.
So I have a philosophical question
Aha.
and a mathematical question. The philosophical question is, if we were to design a robot, would sloths be the starting point? Or are they just a starting point? Or is it... And the mathematical translation of that is that if you want to have any kind of optimality in your UD, then you actually need to solve the MPC problem or something along these lines. Because otherwise you will be violating that constraint all the time. So
I'm going to start with the second one, which is easier. Yes. Right? I mean, the second you want performance, you need to do predictions, right? And so UD would... So here's how I think about it now is UD comes from a optimal controller of some sorts. Could be an MPC, could be something else. And then this thing is just a safety wrapper around it. So 100% agree with you.
You would have to solve that that optimization problem with the safety wrapper.
No, what I would do is I would get rid of that because here... So I want to get back to this idea of long-range autonomy is different from short-range autonomy, where I really think, going back to this idea of nature, we do not move optimally at all. We're not bad over very, very short horizons, but people are not optimal. Animals, turn out, well, maybe they are, but we don't know what they're optimal with respect to. Why should we insist on our robots being optimal with respect to these things that we don't know what they're going to encounter? So it has a different... So to answer your mathematical question in a philosophical manner, I think long range is different from repeatable short range, do things over and over again, or do things in my lab. So I tried to be a little provocative here to say, let's not worry too much about this. And if we solve this, let's solve this without worrying about this stuff and then just add it on. You're no longer optimal. You may be reasonable, and at least you're safe. So that's... But when I'm flying, for instance, so I've done quite a bit of coordinated flight, no way would I do this, right? I would actually solve a problem that involves performance and safety at the same time. But when I have mobile sensor nodes out there, maybe I don't need that. So that was one. Now, let's go back to the sloths. Is it the right animal? So this whole sloth thing started by me being in Costa Rica and just, how can they even exist, right? They're just sitting there waiting to be eaten, right? I mean, how can nature support such slow animals? And it turns out that there are these strategic reasons. So there are eagles that the Harper eagle operates on optical flow. So if you're just slow enough, you become invisible to the raptors. But nature supports slow things. So is it obvious that we should not have slow robots if we're out, again, operating at the time scale of the plants? Why do they need to be fast? They just need to be hyper energy efficient. So I think sloths are horrible examples for robots in almost all applications. But I also think there are applications where slow is fine. In fact, I convinced ONR to pay for what we call robot ecologies, which explores the notion of slowness in robotic systems. So I think there are times when it's good to be slow. But there are also times when it's good not to be slow. So, but by the way, I think sloths are amazing. So guys, do you know why they climb down? No one had asked me that yet.
To To go to the bathroom.
So the path.
Yeah, but why? Why don't they just drop it from where they're sitting?
They'll land on a branch.
Well, so there are two reasons. One is, if you're just sitting there in a tree, it's actually very hard to attract a mate. So what you do is you kind of mark your tree with a pile, and apparently the more bullshit you generate, the more attractive you are to the opposite sex. That's one. And the other is they're covered with these moths that can't fly that help keep the sloths happy and clean. And actually they harvest, or the moths have something to do with this algae that the sloths have on them. But the moths have to also go to a different colony every now and then. So the moths hop down, and then they go to the next pile of sloth dung, and then they jump up on that sloth when it goes down to go to the bathroom. So there is some way of keeping the moth population in your fur healthy and look good to the opposite sex. So, fine. Okay. This guy has been trying to ask a question for a really long time.
So that in that Robotarium, from the user experience, when they are designing, let's say, a controller or a system, is that minimally invasive safety a white box for them, or they have to learn it? Is it changes over time? Like, how is the user experience?
Yeah, so that's a good question. So let's say you randomly show up and you run things on the Robotarium. You just upload code. So by the way, we don't do any checks. So the code is there, and then you don't even schedule time. It just runs when you're up. You end up in a queue. If you just do that, then this thing is just wrapped around it. You don't know it. And then the data you get back are the trajectories of the robots. You can get the sensor data if you want. You get the video feed, and then you get a log that shows how often our safety controller was engaged. Now, if you, for instance, don't want to test you want to test your stuff, not your stuff with our stuff, then you have to convince us that what you're doing isn't crazy. And the way to do that is we have a simulator, and you ask us to run your code in the simulator, and if it looks fine, then we run it without it. If you want it in the air, there are additional layers because stuff in the air, when things break, it breaks for real. But that's what happens on the ground.
Is it possible to attack your system?
Impossible.
If you perturb those parameters, it's possible to enforce like that collision does happen.
Yeah. So one of the things that I was interested in is how do I. So first of all, we got what's called an MRI, which is a major research instrumentation grant from NSF, and then we got a DURIP from ONR, which is another build stuff. Right? So we had money to build it, but I don't just want to build it. I want to do research about it. And the thing that I was most interested in is this question of cyber-physical security here, because people are indeed trying to attack it. And there's a cyber piece, but it's really a physical system, and how do you make sure that it's safe? So yes, it's possible to attack it, and people have actually tried. A, for academic purposes, and B, for just because they're assholes, for malicious purposes. We're recording this. But that's, I have now 2 grants to try to do the cyber-physical security aspect of it to actually detect malicious things. But at this point, I think it is certainly possible to attack it. Our OIT people, our Office of Information Technology, they are not all that excited about the Robotarium. They find it kind of horrifying that we're literally giving people access to physical things on campus remotely.
All right, let's take another question or two, and then we should wrap it up.
Just curious, how did you get into the system area? I know the Swedish, there are many big shots in systems. How did you get into this area?
How did I become a systems theoretician? So I was... First of all, I was actually, weirdly enough, attending 2 undergraduate universities at the same time in Sweden. One, I have a BA in philosophy and linguistics, and I thought I was going to do that. And then I was studying physics at KTH and the Royal Institute of Technology, and I kind of liked it, but I liked the mathy part, and I really thought mathematics was beautiful, but I wanted it to be a little applicable. And then I took this course as a senior on mathematical systems theory taught by Anders Lindqvist, and I thought this was awesome, right? It was beautiful theory, yet it somehow seemed to be relevant to real systems, and I just kind of loved that idea. of thinking hard and deeply about problems and proving theorems, yet having them be applicable. So it was that course. And then I did a PhD with Anders. And but I mean, it's weird. My PhD is in applied math. But I had a robot, actually, in the math department. It was this remote controlled car driving up and down the corridors, and people make fun of me for that. And now, the older I get, the robot to theorem ratio is going way up, right? So I have more and more robots and same number of theorems, let's say. But I started by I love the idea of the mathematical precision and beauty of this, yet it was actually applicable. So I was sucked in that way.
So being a director of the Robotics Institute, you cannot behave like a sloth.
Ha!
Can you do that?
Professors that seemingly do nothing most of the time, right? Minimize U squared. I can. The problem is that my constraints, the survival constraints, are quite steep, right? So the whole institute got to eat. And we don't eat leaves. We eat money. Right? So I do spend a lot. I mean, no, but it's been interesting to take a much broader view of the field when you run a large research enterprise.
So who is your biggest competitor, CMU or MIT?
Yeah, let's thank Professor Egerstedt again.
Thank you.
This was fantastic.